If you were to ask an astronomer which planet in our solar system we understand the least, most would say Neptune without hesitation. It's the furthest major planet from the Sun, shrouded in mystery, visited only once by a spacecraft over 3 decades ago, and difficult to observe even with our most powerful telescopes. Until now. James Webb Space Telescope has just sent back the most detailed images of Neptune we've ever seen. Images that reveal features invisible to every telescope that came before it. Images that show things happening in Neptune's atmosphere that shouldn't be possible. Images that have completely overturned what we thought we knew about this distant ice giant. Strange temperature inversions in regions that should be frozen solid. Atmospheric chemistry that defies our current models. Ring structures behaving in ways that contradict orbital mechanics. And perhaps most baffling of all, evidence of rapid changes happening in real time. Changes that shouldn't occur on a planet this cold and this far from the Sun's energy. Scientists are confused, and that confusion is leading to some of the most exciting research in planetary science today. Of all the planets in our solar system, Neptune is the one rewriting the textbooks. But what exactly did Webb see? And why has it left the scientific community so perplexed? Today, in this deep dive, we're going to examine James Webb's groundbreaking new observations of Neptune, explore the mysteries they've revealed, and understand why this distant blue world is proving far stranger than anyone imagined. Let's start with understanding why Neptune has always been such an enigma. Neptune wasn't discovered the way most planets were, through patient observation with telescopes. Its discovery story is far more intriguing than that. Neptune is the only planet found through pure mathematical prediction. It happened in 1846 thanks to Urbain Jean-Joseph Le Verrier, a French astronomer and mathematician with an exceptional talent for celestial mechanics. Le Verrier had been meticulously examining the orbital motion of the 7 known planets when he noticed something peculiar about Uranus. Its orbit wasn't quite right. Uranus wasn't moving exactly as Newton's laws of gravity predicted it should. The deviations were small, but they were undeniably there. Le Verrier reasoned that the only explanation for these orbital perturbations was gravitational influence from an unknown 8th planet lying beyond Uranus. He performed extraordinarily complex calculations by hand, no computers, in 1846, and declared that this mysterious planet must exist at a specific location in the night sky. He was so confident in his mathematics that he sent his predictions to astronomers across Europe. The incredible thing was, after hearing Le Verrier's prediction, his colleague Johann Gottfried Galle at the Berlin Observatory got out a telescope, pointed it at the predicted coordinates, and discovered Neptune in less than an hour of searching on the very first night. It was almost exactly where Le Verrier had calculated it would be. A triumph of mathematical physics over observational astronomy. Triton, Neptune's largest moon, was discovered just 17 days later. But since that remarkable discovery, Neptune has been frustratingly difficult to study. It orbits at the very edge of what we consider the planetary solar system, at an average distance of 30 astronomical units from the Sun. That's 4.5 billion kilometers, 30 times farther from the Sun than Earth. At certain points in its highly elliptical orbit, Neptune actually ventures further from the Sun than Pluto, though this hasn't happened since 1999 and won't occur again until the 23rd century. The Sun appears only 1/900th as bright in Neptune's sky as it does from Earth. From Neptune's cloud tops, our Sun looks like just a very bright star, hardly recognizable as the brilliant disk we see from Earth. This vast distance and dim lighting meant that for most of history, Neptune couldn't be studied in any detail from ground-based telescopes. Even the most powerful Earth-bound observatories saw Neptune as little more than a tiny blue dot, occasionally revealing hints of atmospheric features, but nothing conclusive. Neptune is the eighth and furthest planet from the Sun, orbiting at about 30 astronomical units, which translates to 4.5 billion kilometers. This enormous distance means it takes a staggering 165 Earth years to complete a single orbit around the Sun. Think about that. Since Neptune's discovery in 1846, it has completed only one full orbit. It won't finish its second orbit until 2011. Because of this immense distance, traveling to Neptune with current spacecraft technology would take approximately 12 to 13 years, assuming you could take advantage of gravitational assists from other planets along the way. All of this makes Neptune exceptionally challenging to study. It's difficult to see clearly from Earth, and visiting it with robotic explorers is an expensive, decades-long commitment. In fact, only one spacecraft has ever visited Neptune, and that mission was only possible because of a rare planetary alignment that occurs once every 176 years. That spacecraft was Voyager 2. It wasn't until August 25, 1989, when Voyager 2 completed its grand tour of the outer solar system, that humanity got its first close-up look at Neptune. The spacecraft had departed Uranus in January 1986, capturing a stunning farewell image from 1 million kilometers away as it set course for its final planetary destination. After 3 years of travel at 54,000 kilometers per hour, Neptune finally came into view. And the images Voyager 2 sent back were spectacular. Here were the first detailed photographs of the giant blue planet, passing just 5,000 kilometers above Neptune's North Pole, the closest approach of any planetary flyby on Voyager's entire journey. Suddenly, we could see what Neptune actually looked like. We confirmed it had a faint ring system. We discovered 6 previously unknown moons. We measured wind speeds that shattered records. And we saw the Great Dark Spot, a storm system the size of Earth churning through Neptune's atmosphere. But Voyager 2's flyby was brief. Just a few hours of close approach. Then the spacecraft continued its journey toward interstellar space. And for over 3 decades, those Voyager images remained our best views of Neptune. Until James Webb Space Telescope turned its infrared eyes toward this distant world. Webb observed Neptune for the first time in September 2022, and again in multiple observation campaigns throughout 2023 and 2024, and what Webb saw has left planetary scientists genuinely baffled. Let me explain why these new images are so confusing. First, we need to understand how James Webb observes planets differently than previous telescopes. Voyager 2 and the Hubble Space Telescope observe primarily in visible light, the wavelengths human eyes can see. In visible light, Neptune appears as a beautiful blue world, its color caused by methane in the atmosphere absorbing red light and reflecting blue. But James Webb observes primarily in infrared wavelengths, heat radiation invisible to human eyes, and in infrared, Neptune looks completely different. In Webb's infrared images, Neptune appears almost ghostly white in some wavelengths, with its rings shining brighter than ever before. The methane that gives Neptune its blue color in visible light actually absorbs strongly in the infrared wavelengths Webb observes, making the bulk of Neptune's atmosphere appear dark. But here's where it gets strange. Certain features in Neptune's atmosphere appear bright in Webb's images. Extremely bright. Brighter than they should be based on our understanding of Neptune's atmospheric composition and temperature structure. These bright features are high-altitude methane ice clouds hovering above most of Neptune's methane absorption layer. We knew these clouds existed from Hubble observations, but Webb revealed them with unprecedented clarity. And they're in the wrong places. According to our atmospheric models, these high-altitude clouds should form primarily in Neptune's active storm regions and around its south polar vortex, where upwelling brings methane gas to high, cold altitudes where it freezes into ice crystals. But Webb's images show extensive bright cloud features near Neptune's equator, in regions where our models predict the atmosphere should be relatively stable and quiescent. No vigorous upwelling, no storm activity, no mechanism to lift methane to the altitudes where these clouds are forming. Yet there they are, extensive, bright, and completely unexpected. Dr. Patrick Irwin from the University of Oxford, who led one of the Webb observation teams, commented in a 2023 paper, "We're seeing atmospheric activity in regions of Neptune we thought were meteorologically dead. The distribution of these cloud features doesn't match any of our current atmospheric circulation models." That's scientist speak for, we have no idea what's going on here. But the cloud mystery is just the beginning. The real confusion comes when we look at Neptune's temperature structure. Neptune's distance from the Sun means its atmosphere is extraordinarily cold. Voyager 2 measured average atmospheric temperatures around -200 degrees Celsius. At those temperatures, Neptune should be a frozen, sluggish world with slow atmospheric circulation. But it's not. Neptune has the fastest winds in the solar system, with equatorial jet streams reaching 2,100 kilometers per hour. Far faster than anything on Jupiter, despite Neptune receiving 900 times less energy from the Sun. Scientists have long suspected that Neptune must have a powerful internal heat source to drive these ferocious winds. Unlike Uranus, which appears to radiate very little internal heat, Neptune emits about 2.6 times more energy than it receives from the Sun. But where does that energy come from? And more importantly, how is it distributed through the atmosphere? This is where Webb's observations become truly perplexing. In 2023, Webb measured the thermal emission from different regions of Neptune's atmosphere in unprecedented detail. And the temperature distribution makes no sense. Neptune's south pole is currently experiencing summer, tilted toward the Sun. You'd expect the summer hemisphere to be warmer than the winter hemisphere. And it is, but only slightly. More confusing, Webb detected a massive temperature inversion in Neptune's upper stratosphere. In Earth's atmosphere, temperature generally decreases as you go higher until you reach the stratosphere, where ozone absorption causes warming. We have a similar inversion layer, but Neptune doesn't have ozone. It doesn't have any known molecule in its upper atmosphere that should cause heating at high altitudes. Yet Webb clearly detected a warm stratospheric layer, with temperatures up to 20 degrees Celsius warmer than models predicted. At an altitude where the atmosphere should be at its coldest, it's somehow being heated. Dr. Lee Fletcher, from the University of Leicester, a leading expert on giant planet atmospheres, stated in early 2024, "This stratospheric warming is one of the biggest mysteries to emerge from Webb's Neptune observations. We've checked for measurement errors, recalibrated our instruments, and rerun our models dozens of times. The heating is real, and we have no satisfactory explanation for what's causing it." Several theories have been proposed. Perhaps auroral activity is heating the upper atmosphere. Neptune does have a magnetosphere and experiences auroras, though they're different from Earth's due to Neptune's offset and tilted magnetic field. But when scientists calculated how much heating Neptune's auroras could provide, it wasn't nearly enough to explain the temperatures Webb measured. You'd need auroral activity orders of magnitude stronger than anything we've observed. Another theory suggests chemical reactions in the upper atmosphere might release heat, Perhaps methane is being broken down by solar ultraviolet radiation in an exothermic process we haven't accounted for. But again, the numbers don't work. The amount of solar UV reaching Neptune is so small that even the most optimistic photochemical models can't produce enough heating. A third hypothesis involves gravity waves, atmospheric oscillations that can transport energy upward from the lower atmosphere. These exist on Earth and other planets, but Neptune's gravity wave activity would need to be far more vigorous than anything we've observed to explain the stratospheric temperatures. And we should be able to see evidence of such strong wave activity in Webb's images. We don't. As of now, Neptune's stratospheric heating remains unexplained. A genuine mystery that our current physics can't resolve. But the mysteries don't stop there. Webb also revealed something extraordinary about Neptune's rings. Neptune has 5 known rings, all named after astronomers involved in Neptune's discovery and early study. The rings are faint and dark, made of dust and ice particles that barely reflect sunlight. Ground-based telescopes struggle to see Neptune's rings at all. Even Hubble can only detect them in long-exposure images under ideal conditions. Voyager 2 saw them clearly during its 1989 flyby, but only because it was so close. James Webb, observing from 1,000,000 miles away, captured the clearest images of Neptune's rings in over 30 years. And they look different than expected. The outermost ring, the Adam's ring, contains several bright arc segments rather than being a continuous ring. These arcs are named Liberté, Égalité, Fraternité, and Courage. They've been known since Voyager 2's observations, and they've always been puzzling. Ring arcs shouldn't be stable. The particles in a planetary ring should spread out evenly over time through collisions and gravitational interactions. Within a few years or decades at most, any clumping should dissipate into a uniform ring. Yet these arcs have persisted since at least 1989, possibly much longer. Something is confining the particles, keeping them clumped in these discrete segments. The leading theory is that a small moon, possibly too small to have been detected yet, is shepherding the ring material through orbital resonance, similar to how Saturn's moon Prometheus shapes Saturn's F-ring. But Webb's new images revealed something unexpected. The brightness and extent of the Adam's ring arcs have changed since Voyager 2's observations. One arc, Courage, appears to have faded significantly. Another, Liberté, appears brighter and more extended than it was in 1989. And there are hints of new, fainter arc segments that weren't visible before. This is strange. If a shepherd moon is maintaining these arcs through stable orbital resonance, they shouldn't be changing this much over a mere 34 years. Orbital mechanics are predictable. Ring arcs in resonance with a moon should maintain consistent structure over timescales of centuries or millennia. The fact that they're changing suggests either our shepherd moon hypothesis is wrong or something more dynamic is happening in Neptune's ring system than we understood. Dr. Imke de Pater from UC Berkeley, who has studied Neptune's rings for decades, noted in 2023, "The variability we're seeing in the ring arcs is difficult to reconcile with our standard models. It suggests the ring system is more active and evolving than we thought possible for such a distant, cold environment." Some researchers have proposed that micrometeorite impacts might be disrupting the rings, creating temporary bright spots that fade as the ejected material disperses. But the scale and duration of the changes Webb observed seem too large for this explanation. Another possibility is that unseen moons, perhaps multiple small satellites, are gravitationally perturbing the rings in complex ways. But if such moons exist, why hasn't Webb detected them? The telescope is sensitive enough to spot objects far smaller than any hypothetical shepherd moons. The ring mystery remains unsolved. Then there's the mystery of Neptune's storms. And this is where things get truly bizarre. When Voyager 2 flew past Neptune in 1989, it observed a massive anticyclonic storm near the planet's equator, similar to Jupiter's Great Red Spot. This storm, called the Great Dark Spot, was about the size of Earth and featured winds up to 2,400 kilometers per hour, the fastest ever recorded in the solar system. Scientists expected this storm to be a permanent or at least long-lived feature, much like Jupiter's Great Red Spot, which has persisted for at least 350 years. But when Hubble observed Neptune in 1994, the Great Dark Spot was gone, completely disappeared, in just 5 years. Since then, Hubble has observed other dark spots appearing and disappearing on Neptune. These storms seem to form, persist for a few years, then dissipate. Unlike Jupiter's stable vortices, Neptune's storms are transient. Webb's observations have added a new layer of confusion to this mystery. In 2022 and 2023, Webb monitored a dark spot that Hubble had discovered in 2018. This storm, located in Neptune's southern hemisphere, appeared stable in Hubble images. But Webb's infrared observations revealed something Hubble couldn't see. The dark spot wasn't just a storm on Neptune's visible cloud deck. It extended deep into the atmosphere, with temperature and chemical signatures indicating the vortex reached down into pressure levels we thought were too dense and stable for large-scale storm systems. Even more strangely, Webb detected rapid brightness variations within the storm over observation periods as short as 6 hours. Neptune's day is about 16 hours long. These variations suggest the storm is evolving on timescales far faster than atmospheric models predict. On Jupiter, storm evolution happens over weeks or months. On Neptune, storms appear to be changing hour by hour. Dr. Michael Wong from UC Berkeley, part of the Webb observation team, commented, "It's as if Neptune's atmosphere is in fast-forward mode compared to Jupiter. We're seeing changes in a single rotation period that we'd expect to take weeks on a similar-sized planet. The energy dynamics must be radically different." But what's driving this rapid evolution? Neptune receives far less solar energy than Jupiter. Its internal heat source, while significant, shouldn't create this kind of atmospheric hyperactivity. Some scientists now theorize that Neptune's atmospheric layers might be less stable than we thought, perhaps with vigorous convection cells transporting heat and momentum between different altitude levels at surprising rates. Others suggest chemical processes might be involved, with methane and other hydrocarbons undergoing phase changes at specific temperature and pressure levels, releasing latent heat that drives rapid storm development. But these are speculations. The truth is, we don't know why Neptune's atmosphere behaves this way. Another baffling discovery from Webb concerns Neptune's largest moon, Triton. Triton is extraordinary in its own right. It's the only large moon in the solar system with a retrograde orbit, circling Neptune in the opposite direction to Neptune's rotation. This strongly suggests Triton didn't form alongside Neptune but was captured, probably from the Kuiper Belt, making it essentially a dwarf planet that became a moon. Triton is geologically active, with nitrogen geysers erupting from its surface. Voyager 2 observed these geysers in 1989, seeing plumes reaching 8 kilometers high. When Webb observed Neptune in 2022, Triton appeared in the background of some images, and Webb detected something unexpected in Triton's extremely thin atmosphere. Temperature spikes, localized warm regions in Triton's upper atmosphere that appeared and disappeared over the course of Webb's observation sequence. These warm spots might be related to geyser activity. If a geyser erupts, it releases nitrogen gas that absorbs sunlight and warms the surrounding atmosphere temporarily, before the gas freezes and falls back to the surface. But the temperature spikes Webb detected were larger and more frequent than Voyager 2's observations would suggest. Either Triton's geyser activity has increased dramatically since 1989, or Webb is detecting phenomena that Voyager couldn't see. If geyser activity on Triton is variable on decadal timescales, it suggests something dynamic is happening beneath Triton's icy crust. Perhaps tidal heating from Neptune is more significant than we calculated. Perhaps Triton has a subsurface ocean that undergoes periodic convection cycles. Or perhaps we're witnessing the long-term evolution of a captured Kuiper Belt object slowly being transformed by its orbital relationship with Neptune. We simply don't know. And that uncertainty is both frustrating and exciting. So where does all this confusion leave us? James Webb's observations of Neptune have revealed a planet far more dynamic, far more active, and far more mysterious than we imagined. A world that defies our current atmospheric models, challenges our understanding of ring dynamics, and raises fundamental questions about how ice giant planets work. Neptune is rewriting the textbook on planetary science, and scientists couldn't be happier about it. Because confusion in science isn't a failure, it's an opportunity. Every mystery Webb has revealed is a clue pointing toward new physics, new chemistry, new atmospheric dynamics we haven't discovered yet. Researchers are now developing new models to explain Neptune's stratospheric heating, incorporating exotic chemistry, electromagnetic interactions, and atmospheric wave dynamics in ways that weren't necessary for our models of Jupiter and Saturn. Others are refining ring dynamics simulations, testing whether previously unconsidered factors like plasma interactions or electromagnetic forces might contribute to ring arc stability. And planetary scientists studying exoplanets, planets orbiting other stars, are paying close attention. Because ice giants like Neptune and Uranus might be the most common type of planet in the galaxy. Surveys of exoplanets suggest that Neptune-sized worlds are extremely abundant. If we don't understand Neptune and Uranus, the only ice giants we can study in detail, how can we hope to understand ice giants orbiting distant stars? Webb's confusing Neptune observations might hold the key to understanding billions of planets throughout the galaxy. So what happens next? Webb will continue observing Neptune periodically over the coming years, building up a long-term data set that will help scientists track how Neptune's atmospheric features, ring arcs, and thermal structure evolve over time. Hubble will continue monitoring Neptune as well, providing visible light observations that complement Webb's infrared views. And there's hope, though no confirmed plans, for a future Neptune orbiter mission. NASA and ESA have both studied concepts for ice giant missions. China has proposed a Neptune flyby spacecraft that could launch in the 2030s. If such a mission happens, it would revolutionize our understanding of Neptune the way Cassini revolutionized our understanding of Saturn. A dedicated orbiter could study Neptune's atmosphere, rings, and moons for years, answering the questions Webb's observations have raised. But even without a new mission, Webb has already changed Neptune science forever. We now know Neptune is not the quiet, frozen, distant world we once thought. It's a place of vigorous activity, rapid change, and exotic physics that we're only beginning to understand. Scientists are confused, but that confusion is driving some of the most innovative planetary research happening today. Because sometimes, the best discoveries are the ones that make us realize how much we don't know. So there you have it. James Webb Space Telescope has revealed Neptune as a world of mysteries. A planet that challenges our assumptions and forces us to think differently about how ice giant atmospheres, ring systems, and moon interactions work. There's still so much we don't understand. How is Neptune's stratosphere being heated? Why are its ring arcs changing? What drives the rapid evolution of its storms? Is Triton becoming more geologically active? These are questions we couldn't even ask before Webb. Now they're at the forefront of planetary science. Sadly, there are no confirmed missions to Neptune on the horizon. Budget constraints and competing priorities mean ice giant exploration remains a distant dream. But the science continues. Every Webb observation, every new analysis, brings us closer to understanding this enigmatic blue world at the edge of our solar system. I hope we eventually send another spacecraft to Neptune. The mysteries Webb has revealed deserve close-up investigation, and although Neptune is incredibly difficult to reach, sometimes the best discoveries are the ones that require the greatest effort. For now, we'll keep watching, keep analyzing, keep being confused. Because confusion means we're learning, and Neptune still has so much to teach us. Thanks for watching. Meanwhile, check out this playlist for more deep dives into the outer solar system. From Uranus's bizarre tilt to the mysteries of the Kuiper Belt, there's always more to explore. I'll see you next time. Keep looking up.